Hi, good morning. So this will be our first official video on the topics under University Physics 41. And before we proceed, I'd like to note that if ever you have questions regarding this video, you may contact me through our Google Classroom. Now, when we study physics, we know that physics is actually about dealing with objects that is actually moving, and we try to examine. We want to know what will happen to the object at later time, and so in order to do this, we need to learn simple concept about how we do the measurements, especially when we want to describe the motion of a certain object with respect to a certain frame of reference. So in this particular video, we will try to review and establish the most important part before learning, before diving into the subject matter, and this will actually help you on establishing your mathematical tools and gearing up your toolkit towards understanding mechanics. Now, mechanics is actually a branch of physics that deals with moving objects, and there are two types of or two branches under mechanics. We have kinematics and the dynamics. Now, in the first stage of our study, that is actually under the midterm coverage, we will mainly discuss topics under kinematics. Now, kinematics is actually a component in mechanics wherein we try to study motion without looking at the reason why it moves. So basically, we neglect the forces. We just describe how the object starts, what are the initial conditions. We look at when the object starts and what is the location, the position, and then we try to describe the informations of that certain object when it tries to move from one point to the other. On the other hand, dynamics, which will be a main part on the finals, it will actually talk about kinematics plus the reason why that certain object is actually moving. So now the concept of forces is in, and we try to make sense why is that object moving that way. So why does the apple falls downward? Why not upward? And by that, the concept of dynamics plays an important role in understanding the fields of engineering, architecture, and etc. So in here, in this particular lesson, we will try to study units and physical measurements. So I hope you will enjoy this video and learn something about it. So this is module 1, entitled Units and Physical Quantities, and in this lecture we will learn about the following outcomes. First, at the end of the lecture, should be able to apply appropriate units of the different physical quantities. Second, describe the accuracy of a measurement by indicating the correct number of significant figures, and justify the dimensional consistency of an equation. Identify the equivalent expression of the magnitude of a physical quantity using unit prefixes, and convert measurements using the correct conversion factor. And finally, should be able to solve practical problems involving conversion, accuracy of measurements. As you may know, physics is an experimental science. That means in here, we always do measurements and try to create a pattern among the observations that we've conducted or we've made. And then when this pattern is very evident, we say that anyone or another scientist from outside the country can actually validate it, and then that's the time that we call this one as a physical law. Now, before we make an observation, we try to define a certain physical phenomenon. And so the concept of physical quantity comes in, and we define this as any number that can be described quantitatively. What are the examples of this? So basically, you have your height, your weight, your momentum, and then the forces. So describing a height which is considered as a physical phenomenon is actually an example of physical quantity. So physical quantity can be categorized as a fundamental and a derived quantity. And for a fundamental quantity, it is defined to be fundamental because of the fact that we can actually define them the way how we measure them. Just like, for example, if we talk about your height or the length, we actually measure it by using a meter stick. Another example of a fundamental quantity is actually your mass. So in this case, I have to emphasize that mass and weight are two different physical quantities. But if we talk about mass, so mass is actually a fundamental quantity, and then we can define mass by actually measuring it using a weighing scale. And so for the other type of quantity, for the derived, are actually quantities that can be defined by combining these fundamental quantities. Like, for example, for the case of the weight, so later on we will learn that weight is nothing but the product of mass, which is actually a fundamental quantity, and acceleration due to gravity. So acceleration is another derived. So the combination of mass times the acceleration due to gravity creates weight. So that's why weight can be categorized as a derived physical quantity. For momentum, momentum is also a derived quantity, since we know that momentum is nothing but the product of the mass and the velocity. So basically, we can distinguish fundamental from derived by looking at the constituents of that quantity. So like, for example, we just have to take note that for fundamental quantities, there are only three important quantities that you should remember. First is you have the time. So we measure time by using a stopwatch or a clock. And then the length. So we measure length by using a meter stick or a ruler. And then we also have the mass using a weighing scale. And so when we combine these things, we create actually derived quantities. So when we talk about acceleration, so we know acceleration is just change of velocity with respect to time. So you have velocity at the numerator divided by time. So time is a fundamental quantity. Velocity, on the other hand, is actually a derived quantity, because velocity, from its definition, we have distance over time. So distance is in terms of length over time, and then you divide it by time to create acceleration. So that's why acceleration is also a derived quantity. In this part, I want to emphasize that physical quantity is actually important, or using unit is actually important, because when we describe certain physical quantity, like for example the height, so we describe height by using these numbers and letter. So we have 1.91 meter. Now, if we describe this height by just saying that height is 1.91, so we say that it's incomplete. No one can actually understand you, because 1.91 is what? So you need to accompany that number by a unit. So a number plus a unit, in this case, which is actually meters, gives meaning to the physical quantity we call height. So when you describe your height and say my height is actually 1.91 meters, and so that completes the message of your physical quantity. Now there are actually two systems of units that we usually encounter. First, we have the SI units, or the System International, and the English system. So for the examples of the SI units, so we have actually the following. So like for example, in terms of mass, we have a kilogram, and the symbol for that is actually kg. And then for electric charge, the unit used to describe electric charge is actually coulomb, and that is actually denoted by capital C. Now, for the other type of units, we have the English system with the following examples. You have the inch, the pound, the foot, fortnight, slugs. And by this, since we know that physics is actually an experimental science, and so when we made observations, when we conduct experiments, it is important that other scientists from other countries can actually validate your experiments. And to do this, one should be able to convert one unit to the other. Like for example, in the scientific community, we usually talk about physical quantities expressed in terms of SI units. But for the case of those scientists that actually use English system as their commonly used units, so they need to convert their data to SI units. Then how are you going to do this? So you need to master or practice how to do conversions. Now, for conversions, all you need is to take note of the common conversion factors. So for example, if you have, if we talk about distance, so when you go from SI to English, so you need to know that 1 mile is actually equivalent to 1,609 meters, or that is just equal to 1.609 kilometers. And also you need to know that 1 kilometer is of course equal to 1,000 meters, and then 1 feet is actually equal to 30.48 centimeters, or that is just equal to 12 inches. 1 inch is equal to 2.54 centimeter, and so on. So in doing conversions, I have actually summarized at least 4 categories under this. So these are the 4 categories of doing conversions. First, I call this as the direct relation. This is actually an example wherein you have familiarized certain conversion factor, and you are converting certain physical quantity that can be related directly by a certain unit. So I'm talking about when we convert 8 kilometers into miles, and then assuming that you only familiarize 1 mile is equal to 1,609 meters, or is equal to 1.609 kilometers, and so on. So bottom line is, if you can actually familiarize bunch of conversion factors, that's a plus thing. But it is not necessarily follow that if you can actually memorize as much as many of the conversion factors, then you can do actual conversions easily. So the thing is, if you only know this, for example, and then you need to convert 8 kilometers into 1 mile, and so under this category, this is actually direct relations, because kilometers here in your conversion factors, okay, so you have actually in mind that kilometer, you have 1.609 kilometer is actually related directly to 1 mile, and so we can actually perform immediately the calculations. Actually, you need to write on the left hand side 8 kilometers, and then write equals, and then just copy again 8 kilometers, and then the next one is actually you need to multiply the conversion factors. So in this case, since I am converting kilometers to miles, so I have this conversion factor here. I have 1 mile is equal to 1.609 kilometers. So I have to write the conversion factors here, noting that the kilometer is actually on the numerator. So I have to write kilometers at the denominator. So I have kilometers. The purpose of this is actually we need to cancel out kilometers in the numerator. So going back, kilometers in the denominator, and then I have here mile at the numerator. So I have in mind that 1 mile is actually equal to 1.609 kilometers. In this equation, I am just trying to rewrite 8 kilometers. So I have here the left hand side equals the right hand side. So does that really make sense. So is the right hand side really equal to the left hand side? So notice that if you try to focus on this factor here, this conversion factor, this length on the numerator is exactly the same by this denominator. So meaning if I have to divide this length by the amount of length at the denominator, that exactly cancels out that length. So that means this entire factor is actually just equal to 1. So 1 times certain number is just that number. So I'm not changing the validity of this physical quantity, but I am only changing the form. So going back here, I have kilometers in the numerator multiplied by miles over kilometer. So bottom line is I can actually cancel out the kilometers at the denominator. So then you can multiply numerator to numerator. So I have here 8 miles divided by 1.609 at the bottom. So I have no unit at the bottom since I already canceled it out. So simplifying this further means that you just have to divide 8 by 1.609, and that produces 4.972 miles. So that's actually the answer. For the case of indirect relation, this is actually an example wherein you are converting a certain quantity, in this case you have 8 kilometers, into feet, which is actually not directly related based on your familiarized conversion factors. So again, I want to emphasize that at the bottom, these are the conversion factors that you've familiarized. So in relation to this, feet is actually not directly related to kilometers based on the bottom. So in this case, I have kilometers here is related to meters. So I have, and then I have a meter going to feet. You need to perform 2 conversion factors. On this part here, you also have 1 meter to feet. So bottom line is when you solve this, or when you convert 8 kilometers, you need to multiply simultaneously 2 conversion factors. So that's why I call this as the indirect relation. So to solve this, we have, again, just copy 8 kilometers. That should be equal to 8 kilometers, and then multiply the first conversion factor. That is actually conversion factor relating kilometers into meters. So in this case, I have kilometers into meters. Again, the bottom line is kilometers should be placed at the bottom since we want to cancel out kilometers here at the numerator. Now, the conversion factor says that 1.609 kilometers is equal to 1,609 meters. Now, we simultaneously multiply the next conversion factor. So I have now kilometers going to meters. So I have kilometers here, and then I have kilometers also at the denominator, so I have only a meter. So now the only thing left is to convert a meter to feet. So that can be done by multiplying the next conversion factor, which is actually meter relating it to feet. So take note that from here we have this relation, meter going to feet. So I have 1 meter is equal to 3.281 feet. So again, this is 3.281 feet. So now I can cancel out the meter at the numerator and cancel the denominator here, and that reduces 8 times 1,609 times 3.281 feet all over. I have the denominator, which is actually 1.609. So now when you take the product of the numerator and then divide it by the denominator, you'll get roughly 26,247 feet. So that's actually the final answer. The third category is all about converting physical quantity that has fraction. This is particularly encountered when we deal with speed. Now, if we want to convert 8 miles per hour into meter per second, again, all you have to do is to remember the conversion factors that we had earlier, and then we proceed by doing the solution. That is actually we write 8 miles per hour and then copy it, so you have 8 miles per hour. Now we convert first the numerator, that is actually converting miles into meters. By doing that, so we know already that a mile is directly related to meter in our conversion factor. In this case, I have 1 mile. It's actually equal to 1,609 meters. So from that, I can actually cancel out the miles at the numerator here, and then denominator on the conversion factor. Now we are left with converting hours into seconds. Notice that hours is actually at the denominator, so we multiply simultaneously the conversion factor relating hours into seconds. So in this case, we have 1 hour is equal to 3,600 seconds. So we write 1 hour in the numerator and then 3,600 seconds on the denominator. So here we cancel out the hour in the numerator by the hour at the denominator on this part. So we are now left with meters in the numerator and seconds in the denominator. So that's the unit that we want. All you have to do is then simplify the right hand side. That is actually you multiply 8 times 1,609 meters divided by 3,600 seconds, which is actually equal to 3.58 meters per second, or that is roughly equal to 4 meters per second. So that's the final answer. Again, the last category is physical quantity that involves power. So in this case, we have this density, which is actually 1,000 kilograms per cubic meter is equal to how many grams per cubic centimeter. So in this case, I have a power of 3 and a power of 3 for the centimeter. So to solve for this, we need the following conversion factors. Of course, it is basic that we know already the conversion factor of kilogram going to grams and then meter into centimeter. We write left hand side, that is actually 1,000 kilogram over cubic meter, and then again copy it, so you have 1,000 kilogram per cubic meter. So we want to convert first the numerator, that is actually converting kilogram into grams, and since we know that 1 kilogram is actually equal to 1,000 grams. In this case, since the kilogram is in the numerator, we write the kilogram in the denominator for the conversion factors at the bottom. That is actually 1 kilogram is equal to 1,000. So we can now cancel out kilograms here and there. Now, for cubic meter, notice that we don't have a conversion factor that actually relates a unit with a power to another unit with a power. So in this case, you don't have a conversion factor that relates cubic meter into cubic centimeter. So how are we going to solve for this? Now, to do that, you just have to remember that although we don't have those conversion factors, we knew that 1 meter is equal to 100 centimeters. And so we try to multiply this conversion factors. That is actually, we write a meter here. 1 meter is equal to 100 centimeters. Now, the problem is that I have here the power of 3 and I only have the power of 1 here, an imaginary equal to 1 power. So what you do is actually we try to raise the entire quantity by the power of 3 such that we can actually cancel out the power of the 3 here in this part. We distribute this, so we have here and there, and then we also have here and there. So basically we have 1,000 times 1,000 copy grams times 1 cube meter cube, and then at the denominator we have 1 times 100 to the power of 3, and then you have centimeters to the power of 3. So notice that here this is actually cancelled by the meters at the denominator, which is actually found here. So I have that one. So now I have 1 raised to the power of 3 is just equal to 1, and this 100 raised to the power of cube is just equal to 1 million. So basically 1,000 times 1,000 here, that is just equal to 1 million. So this produce 1 million. But I have 1 million here at the denominator, so I can just cancel out 1 million here and 1 million there. So basically we are left with 1 at the numerator divided by 1 at the denominator. That produces 1 grams per cubic centimeter. So that's actually the final answer. Performing calculations with large numbers are actually difficult since it makes the entire process long. So to make this easy and simple, we need to learn how to rewrite those large numbers into prefixes. So in this case, we have actually units or unit prefixes that is useful to rewrite certain large numbers. Like for example, if you have kilo, so every time you encounter 1,000, in this case I have 1,000 grams. So all you need to remember is that 10 to the power of 3 is equivalent to kilo. In this case, I can write 1,000 grams into 1 times 10 to the 3. That this is actually a kilo, so that I can write it as 1 kilogram. So bottom line is, all you need to do is actually remember that every time you see kilo, that's actually times 10 to the 3. And then for mega, that is actually denoted by capital M, that's actually times 10 to the power of 6. All the way to, we have tera. So if you have a hard drive that has 1 terabyte, so tera means times 10 to the power of 12. So the symbol for tera is actually capital T, so you have 1 terabyte is just equal to 1 TB. Now on in the small region, we also have times 10 to the power of -1, that's actually DC. And then for centimeter, we have times 10 to the -2. So that's why if you have 1 centimeter, that's actually 1 times 10 to the -2 of a meter. So notice that centi here is translated into times 10 to the -2 meters. So 1 centimeter is equal to that. And we also have nano, that's actually times 10 to the -9. And we denote nano as N. And lastly, we have also for pico. So you have pico is actually in terms of times 10 to the -12. And we denote it by lowercase p. So that's unit of prefixes. So every time we encounter them, we remember all these things. Now we move to the concept of scientific notation. So this is actually related to unit prefixes. So since earlier we've learned how to use prefixes, so notice that in this case we actually have the form of a scientific notation that is actually, we have this times 10 to the e. So e here is actually the power or the exponent. So in this case, if you have times 10 to the 3, so we know that that's actually kilo. So that's why this is somewhat related to unit prefixes. So now, but you have to remember that for scientific notation, this is actually useful when we want to write large numbers or very, very small numbers easily. So you just have to remember this concept on how to write it. So we first familiarize these general expressions. So we have here C.MMMM. So here C is actually the characteristic digit that is actually rated from 1 to 9. And then you have M, or the mantissa digit, that is actually rated from 0 to 9. And E, of course, the power. So now, if we have a certain number, for this case, we have 98,067.5321. So if we try to rewrite this into scientific notation form, all you have to remember is actually to write this or rewrite this into this form. So we have a digit dot the mantissa digit times 10 to the power p. So in this case, we have the period is actually found here. All we do is actually we try to count how many decimal places when we move this digit going to the left. So this actually, that's 1, 2, 3, 4. So okay, so that's actually the form here. So in this case, so we have the power of 4, and so we try to rewrite it in this way. So you have 9.80675321. That's basically copying it, and then you just have to multiply this by or times 10 to the 4. So that's actually the decimal places that you move to the left. Or roughly, this is just equal to, okay, try to round this one. This is actually equal to 9.81 times 10 to the 4. This is actually the case when you try to rewrite a large number, that this falls under rule number 1. Now, how about when we try to rewrite very small number? So in this case, we have rule number 2. So for example, if I have 0.0000084, so how are you going to rewrite this in terms of scientific notation? So again, we need to take note of this form. So we need to write the dot right after a characteristic digit C. So in this case, the characteristic digit C, that's actually a non-zero number. In this case, we have 8. So all you have to do is move this decimal point here to here. That is actually you count 1, 2, 3, 4, 5, 6. So basically, so you have 6. So you have 8.4 times 10. And notice that I have here 6. I placed negative since we are actually rewriting small numbers. So the rule is actually when you move the decimal places to the right, that is actually corresponds to negative power. So that's actually a scientific notation. Now, since we know that physics is an experimental science, so we always do measurements, we always perform experiments, but we have to remember that when we measure something, there is always an uncertainty and accuracy to what we actually measure. So in particular, when we perform certain measurement, we know that there is uncertainty found in it. So what you do is actually try to minimize that uncertainty to a certain acceptable range. So in your laboratory, we actually agree that when you have this range of error, it is actually 10%. That's actually acceptable. But you have to take note that if your experiment will later on you want to publish it, so that's actually 10% error is a very big one. So you need to minimize it down to small percentage error. But one thing you have to remember is actually how we define accuracy versus precision. So accuracy is actually defined as to how close is that measurement to the standard value, while precision is actually the repeatability of that measurement. So this is actually the definition of precision and accuracy. And precision is actually the repeatability of your measurement. So in this case, suppose you play dart, and then this black dots here are actually the position of your dart pins. When you notice that on the upper left, we could say that measurement is actually it has low precision and low accuracy, because the pins, the black dots, are actually far from each other. Also, they are far from the center, which is actually the standard. Now, moving to the upper right, so notice that all the black dots are actually closely positioned, but they are far from the standard. So we say that this measurement is actually not accurate, but they are precise. On the bottom left, we have actually good accuracy. So you see that the black dots are close center or to the standard, but then the precision is not that good because they are relatively far from each other. So we say that this is actually a high accuracy and low precision measurement. If we try to look at the bottom right, notice that the black dots are actually closely positioned to each other. So we say that this is actually precise, and also this is actually accurate because the black dots are found in the center or the true value. So that's the distinction between precision and accuracy. So we know already that when we do measurement, there is always uncertainty acting into it. And so when we try to write this measurement, we can actually emphasize it through significant figures. So how do we write quantities emphasizing the significant figures? So here are the basic rules on how we write significant figures or determine the significant figures. First, all non-zero digits are significant. So in this case, we have 4 significant figures since we have 4 non-zero digits. 3.67, so we have 3 significant figures, and then you have 3.14, 16, so you have 5 significant figures. Next is zeros appearing before non-zero digits are significant. So here we have 0 appearing in between non-zero digits. So you have 3 and 9. So this is always significant. So in this case, we have 1, 2, 3. So that makes it 3 significant figures. Also, we have here 1, 2, 3, 4, 5, 6. So you have here 6 significant figures. And also with this one, you have 1, 2, 3, 4, 5, 6, 7. So you have 7 significant figures. Next rule is actually zeros appearing before non-zero digits are not significant. Meaning, if I have a digit here, 0.00, so these are not significant. So you don't count this. But then you only count this one, 8, 7, 6. So you have 3 significant figures. So the same thing for this one. So you have 1 significant figure. And here we have 3 significant figures. Next rule is actually zeros at the end of a number and to the right of a decimal point are significant. So that means I have here 76.00. So the zeros here are always significant. So you have 4 significant figures. Same with this. So you have 1, 2, 3, 4, 5, 6. So you have 6 significant figures and so on. For the last one, so you have zeros at the end of a number without decimal point may or may not be significant. So depends. So that's significant figures. I think all you need to do is remember the following examples and these rules. So we apply those concepts that we've learned about significant figures. Now, how do we add or subtract and multiply significant figures? So in this particular point, we need to learn how we add significant figures. So in this case, suppose I have 5.67 meters, and then you add this with 8.1 meters, and then you add this by 0.09378. So the rule is actually simple. all you have to do is actually write the sum by following the decimal places of a certain addend with the least number of decimal places. So in this case, you have 8.1. This is the quantity that has the least number of decimal places. So, answer would be, you need to rewrite this in terms of one decimal place. So that's actually 14.7 meters. So you round off this quantity. So to do that, you need to look at the digit right after 7. This is actually the least number of decimal places. So if this is greater than or equal to 5, so you add 1 here. But if this is less than 5, so you drop this one. So in this case, so we drop this. That means we have 14.7 meters. Now, for the case of multiplication and division, so all you need to remember is actually you just have to follow the entry which has least number of significant figures. In this case, so this part here has the least number of significant figures. So this is 3. This part you have 4. So your answer should be expressed in terms of 3 significant figures. So you need to round off this one. So in that case, so you have the 3 significant figures as in this part. So you need to round off this one. So in this case, 5 is actually higher or greater than 5. So you need to add 1.7. So that makes it 66.8 meters squared. So the same thing for division. So all you need to do is you just follow the entry which has the smallest or the least number of significant figures. So that should be the significant figures that can be found on the quotient. So that's it. I hope you understand these concepts, and thank you for listening. I hope that you learned something from this one, and if you have questions, you can always comment on our Google Classroom, or you may also email me at my email address. Thank you so much.